Thank you, Stefan. Thank you, Filippo. So I'm very happy to be here and tell you about Bandit convex optimization and regret analysis in general. So I have divided the course into 4 chapters, and the first one will be just a general introduction to regret analysis. So I will just start with the framework and then give you a brief overview of what we're going to do over those 10 hours. Okay. So chapter 1 is going to be introduction to regret analysis. And of course, in the spirit of this being a mini course, and also since it's a small room with a small audience, please interrupt me and ask me questions. Really, that will help me a lot to clarify if anything is not clear, and also it will slow me down a little bit. I mean, the blackboard is also slowing me down, but this would be helpful. Okay, so let's start with the framework. So the framework goes as follows. So essentially, in regret analysis, in online learning, what we're doing is that we're playing a sequential game. So we are a player. So we're going to play a sequential game where at every time step we have to make a decision. So for each t, from 1, 2, etc., up to some capital T. Capital T is going to be the time horizon, which I assume is known, but it's not absolutely necessary. So at each time step, the player selects an action. I sub t in 1 to n. Okay, so we have little n action that we can play, and at every time step we have to choose one of them. And simultaneously, there is an adversary that selects LT, a loss function, from the set of actions to the interval 0, 1. Okay? So to every action, the adversary assigns a loss. Okay? So for each action, he says, okay, if you play that action, that's how much you lose. Okay? If you prefer to think in terms of reward, you can also think in terms of reward. That's fine. I will assume most of the time that the losses take value in 0, 1, sometimes between -1 and 1. There is a small technicality whether you allow negative losses, and I will point out these technicalities. Okay, now I want to make something clear, is that IT, the action that you select, is going to be selected at random. So IT is going to be selected at random from PT, where this sampling is independent of the past. Sampling independent of the past. Of course, independent of the past given PT. And PT, this is going to be an element of the simplex. Okay, the n-dimensional simplex, which is just the set of points in R plus n, so that the sum of the xi is 1. Okay, so really, in terms of algorithm design, what I will need to tell you is how do you select this probability distribution as a function of the observation that you have seen so far. Now, what are the observations exactly? So the loss suffered by the player is LT of IT. And of course, what will be the objective of the game? The objective of the game will be to minimize the cumulative loss, okay? To minimize the sum of the losses over time. That will be the objective, to experience as small loss as possible. Now, what is the feedback? We will consider many versions of this game and many versions of feedback, but the 2 canonical ones are full information and Bandit. So in full information is not a great name, by the way, but okay, we're stuck with it. In full information, you observe LT. So at the end, okay, at the end of the round, once you have selected your action, the adversary has selected his loss, we get to observe the full loss function. So we can reason about what would have been our losses if we had played some other action. In Bandit, you're not allowed to do that. In Bandit, you only observe the loss of the action that you played. Okay, so Bandit is simply LT of IT. Okay. I will also think of this LT often as an n-dimensional vector, obviously. Okay, in 0, 1 to 0. So these are the 2 types of feedback. That's what you observe. our goal, again, is to minimize the total sum of losses. And to make the problem meaningful and to prove statement and guarantees, what we need is to have some kind of benchmark. The most basic benchmark, but not necessarily the best one, we'll talk about other ones, is a regret with respect to the best action in hindsight. So if you knew in advance all the losses, what would have been the best action to play, the best fixed action? So benchmark for a good chunk of the course is going to be, I will call it I star, which is the argmin of the sum of the losses. So the sum of LT of I for t equals 1 to capital T, I. Okay, so given all the losses, what would have been the action with the smallest total loss? Okay, and the regret? The regret is exactly the difference between the loss of I star, the cumulative loss of I star, and our loss. Okay, so let me define capital LT, which is the loss of the algorithm. So it's the loss of the player, the sum of LTIT for t equals 1 to capital T. And L star T is going to be the sum of LT of I star. Now the regret is just this difference. So it's LT minus L star T. Okay? Yes?
Is it more reasonable to think of hindsight optimal action which depends on time because they we are taking
Yes. So, of course. So one, the obvious, criticism to this is that I'm allowed to change my action every time. So why am I not allowing, the adversary to change its action? The opt to change its action every time. So we can do that, and we'll do that at the end of the second lecture, so at the end of the day today. That being said, this is still a very meaningful benchmark. You can think that the mindset you have to be in is the machine learning mindset. So what is the machine learning mindset is that a single loss function does not tell you much about what is a good action. But if you look at the loss function, in their globality, then there is some good actions that emerge. So if many of you are interested in machine learning and say optimizing deep nets or things like that, so you can think that if, finding the good parameters for your deep net, a single image is not going to tell you much about what is a good set of parameters. But if you look at a big data set of images, if you look at a group of images, then maybe you can find a good set of parameters. What is the analogy with this? Right now we have a finite action set, but very quickly we're going to move to a much larger set of actions. And the set of actions could actually be the parameters of your deep net. Okay? And the loss function is really telling you on a given image, so you can imagine there is an image coming at you. On this image, if you use those parameters, how well do you perform? So this is the mindset that you have to be in. Okay? So very soon, this question really is pointing to the fact that you shouldn't think of this as a small set. Very quickly, it's going to be a very large set, maybe with some structure, and the losses also themselves will come with structure, and then it makes more sense. Okay? Now I'm going to add a small subtlety, which I hope you ask me questions about it, because I know it confuses everyone all the time. So to simplify, notice that these losses, they are random. Okay? Why are they random? The adversary is reacting to us, okay? And we are playing actions at random. So depending on the realization of this random variable, the losses might become different. Okay? So this thing is a random variable. Now, it's nicer to work with the expectation of this random variable. Just working with the expectation is a little bit tricky because then I star is also random. This is doable, but to simplify in this course, what I'm going to do is that I'm going to put an expectation here. Okay, so I'm taking the best action in expectation. Okay. Similarly, here I'm going to put expectations. Okay. So this is my definition of the regret. Does that make sense? Is it clear? And despite what I just said, for most of what we're going to talk about, you can think of an oblivious adversary. So remark. So think of an oblivious adversary. Really, I think you shouldn't think at all in terms of an adversary. Okay? It's not like there is somebody trying to trick you in making the regret big. You know, there is some process. You know, nature is doing something which is producing those losses, and you do not have control over it. And the key point of this model is that you don't want to make any stochastic assumption about those losses. You certainly do not want to say that they are IID or anything like that, okay, which is a standard assumption in machine learning, and it's a very clearly wrong assumption. It allows us to develop statistical learning theory, but it's not a good model for real life. Even if you think of a data set of images, you know, these images were collected in some ways, there is some bias, you know, two data sets, they are always different, so this is not a valid assumption, and the whole point of this theory is to go beyond that, okay? Now, the point of the theory is not really to go against an adversary, okay? Because if you really think of an adversary, this quantity does not make sense, because this quantity does not represent what would have happened if I had played a fixed action all the time. If I had played a fixed action all the time, then maybe the adversary would have reacted differently. Okay? But if you follow that route, then you get into what is called policy regret, and you cannot really do much. Okay? So really, we don't want to think of the adversary. The adversary is just a modeling assumption, if you want, or a lack of modeling assumption. So think of an oblivious adversary, which means L1 through LT chosen at the beginning. That's what it means. Okay. And the regret, one way you can think of it, so remark, the regret, let's say divided by T, is the rate at which I star is identified. Okay, so again, coming back to the question before, you can think that, really think of this as playing in an unknown environment. There is this unknown environment, you're making sequential decision, and the unknown environment is represented by this sequence of loss function. And as you play, you discover more and more of your environment, and what you hope for this to be meaningful is that there is a good action to be found. Okay, in this environment, there is some good action to be found, but it's complicated because, you know, some rounds, maybe the loss functions, they are telling you nothing about what is the optimal action. Maybe they are even confusing you, and you have to discard all of this noise to really focus on the signal. Okay, that's what all of machine learning is about, to try to extract the signal out of this sequence of losses. And really, the regret divided by T is simply the rate at which you identify I star. Okay, so for instance, it makes sense to ask questions like, how big needs T to be so that this quantity is epsilon? And then this means that once you have played that many rounds, no matter what the environment is doing, you have identified the good action up to an error of epsilon. Okay. Now, one more thing that I want to say about this regret notion is that, of course, it could be that this doesn't make sense, that there is simply no good action, okay? In which case, the regret is not meaningful. So a key point of the regret analysis is to say that if there is a good action, then you find it. But if there is no good action, if everybody is paying, you know, and there is nothing good, then of course you're not going to be good either. So that's one of the points of having a benchmark. Okay. So some applications. So this series that we're going to develop and the algorithms that come with it has been very successful in the last 10 years, 10, 15 years. So the main one, you know, the one that makes money is ad placement. So in ad placement, what you are thinking is that the player is running a website and the set of action is a set of ads, okay? Now, every time step, there is a user that comes, and what you have to do is you have to choose one of the ads, okay? And you choose one ad, and then this is really appropriate for the Bandit framework. You choose an ad, and then you see whether the user clicks or not. But you don't see what would have happened if you had presented another ad. Okay, so ad placement is really key. And you can see with this application already that there is a big aspect of this problem which is missing. Namely, when a user comes, usually you have some information about the user. Maybe the user is logged in on your website, or maybe he came on the website through a query on Google or Bing. So you have some contextual information about the user. This will come in the contextual Bandit problem, where in addition, at every time step, there is also a context which is revealed. And now you're going to compete not with the best fixed action in hindsight, but the best mapping from context to actions. So again, coming back to what you were saying, this is going to expanding the benchmark, competing with something stronger. One thing is this packet routing. So you imagine that you have a graph, you have some source node, some target node, and what you want is to send some packets, in this graph. And every time step, what you have to choose for each packet, you have to choose which path you take, to send from S to T. So now in this problem, the set of actions is huge. It's a very, very large action set. And, but it has a lot of structure, so there are exponentially many paths, maybe from source to target, but two paths, if they can be close to each other. There is some notion of metric, some notion of distance, okay? So this will be a great example of a large set of actions, but which comes with structure. And we will talk a lot about this. Let's see, which other application do I want to tell you about? Oh, yeah, of course, hyperparameter optimization. This is a really popular one. And here I should say, in both of these, it makes sense to not make an IID assumption, right? You don't want to say, the packet routing, maybe there are many other players playing on this graph, sending themselves signal on the graph, creating some congestion. And it's a very non-IID process because they are also reacting to what everybody is reacting to everybody. So you don't want to say that you are in some kind of stationary mode, okay? On the other hand, when I say that, the lack of stationarity also points to maybe a best fixed action is not good. So all of this we have to talk about. But this is really the canonical framework. Hyperparameter optimization. Okay, I don't want to dwell too much on it. One big one is, I would just say AI for games. And by this, I really mean efficient tree search. So all of you have heard about AlphaGo. And of course, Bandits did not solve AlphaGo, just to clarify. But it was, for real, a key component of the algorithm. Why was it a key component? Well, one of the big idea, going back to 2005, is to add randomness in the algorithm. Okay, so Go is a deterministic game, but it makes sense to add randomness just to search more efficiently. So the randomness is added in what is called Monte Carlo tree search. So what you want is you have this big tree, and you want to explore it efficiently. And what we're thinking of this tree, the leaves of the tree are our set of actions. And what you want is just to efficiently explore this set of action. And what people use are Bandit algorithms to explore this tree. So this is one application. And again, it's a structured set. So all of this, you see, every time you have structure, you have context. Maybe you want to compare to a more complicated benchmark. But all of these, refinement, they all rest on this fundamental theory. So the first chapter is going to be focused on this, and then we will expand to these more applicable problems. Okay. So let me just say again an overview. Okay. So overview of some of the results that we're going to talk about. So first, we will talk about full information with finite actions. So there, what are we going to show? We'll show, first of all, that the regret has to be at least square root t log n. And by this, I mean that no matter what strategy you have, there is a sequence of loss functions such that your regret is that big. Okay? And this situation is going to be for pure noise. I will make this mathematically clear, but I prefer to give you some English words first. So pure noise will mean that the past does not say anything about the future, right? I mean, what's the point of this game is that you want to use past information to guide you for your future choices. But it could be that the past is just irrelevant for the future. Everything is completely random. If that's the case, then we will see that the regret has to be square root t log n. So that's like a lower bound on what you can hope to achieve. Then we'll show that, in fact, there is an algorithm, so there exists an algorithm, such that the regret is always at most square root t log n. Okay. Meaning that this is the only obstruction to having a small regret. Whenever there is signal in the data, this algorithm will pick it up, because in a sense, it matches exactly the lower bound. Okay? It gets the best possible thing. Now, a natural question you might ask is, okay, this is the best you can do for pure noise, and here you're showing me that, okay, we can always match this bound, but maybe if there is more signal in the data, maybe you can do better. Okay, so this will be another topic that we will touch on. So this, we will see two proofs of this today, I mean, right now, in the next 2 hours. So one of them is going to be algorithmic. I will show to you an algorithm that achieves this. It will be a bit magical. And then I will show you a much more principled approach based on game theory and information theory that really explains to me why you can get this. And this log n is really going to be an entropy term. Okay, so this we will see it in the information theoretic analysis, and in the second lecture today, we'll see an algorithm which is inspired from this information theoretic understanding. Okay, good. So the next topic, another topic that we will touch on is easy data. And by this I mean, maybe can you characterize how difficult is your sequence of losses? You know, is there more signal in the sequence of losses than there would be in pure noise? So I will just give you an example. It's going to be a bound where the regret, just to give you an example of what I have in mind, this is a bound which is going to be look like this, square root of L star t times log n. So this L star, remember, it's the loss of the best action. So what this is saying is that if really there is an action which is very good, which has a very small loss, then in fact our regret is going to be much smaller than before. Okay, of course, L star t is bounded by t. So this is a type of bound that shows to you that if there is some easiness in the data, if there is more signal than what there is in the pure noise situation, then you can do better. But this is just an example, and this is a mini field, you know, with workshops organized at basically every year at the machine learning conferences. So there are many, many things to be said about this, and maybe I will tell you a bit more. Then there will be Bandit. So let's say Bandit with finite actions. So there we will see that the best regret that you can obtain is of order of square root Tn. Okay? So you see, instead of this log n, now the number of actions comes linearly, I mean polynomially, okay, as a square root n. So this is so this is necessary. We will see that you cannot do better. You see it's a theta, so it's both an upper bound and a lower bound. You cannot do better than this. But it's very, very bad news for all the applications we are talking about. Whether, you know, it's this setting where the actions are the leaves of a tree, or it's this one where you have, you know, millions of ads, or packet routing where, you know, the number of ST paths is going to be exponential in the size of the graph. So in all these applications, it would mean that for this to be smaller than epsilon, when I normalize by t, you need, you know, at least n samples, which makes sense. I mean, before you have seen n rounds, you don't even have seen every entry of a loss vector. So of course you cannot do anything. So the next point will be, what can you do when you have a large action set but which is structured? Okay, so large and structured action sets. So this will be a big chunk of what we'll do. So so this will be essentially lectures 3 and 4. And we will briefly talk about this also today. Maybe I don't want to say too much about it right now, what I have in mind. And of course, eventually, what is the end goal of the course? The end goal, the star of the course is going to be what can you do when you have a continuous set of actions. Okay, so it's a subset of, let's say, n space. And your losses are convex functions. Okay, so now, in this situation, at this point of the talk, if you have never seen Bandit, it really seems hopeless. I mean, you have this very high-dimensional set, and you have this, high-dimensional function, and you just see a single point on this function. What can you say about everything else? And we'll see that you can say almost this. You will almost get this bound, where n is going to be the ambient dimension. Okay, so this will be the end. So this will be lecture 4, where I will describe an algorithm which has many connections to some nice topic in mathematics. So just let me tell some keywords for those of you who know about this. So we'll see Bernoulli convolutions appearing. We'll see geometry of log concave measures. Okay. And many other things. This is just to get you interested. Another thing that we'll do is better benchmark. So this, we'll talk about it today in the second chapter. So this will be chapter 1. This also will be chapter 1. Better benchmark, we will talk about it this afternoon. So again, this is the case where you want, maybe you go crazy and you want to compete with something that can switch all the time. You can do it, but then you shouldn't talk about regret, but competitive ratio. And then you get into the field of online algorithms, and I will mention some key problems there. Okay, so I think that's all I wanted to say for the overview. Is there any question before I tell you an algorithm, a magic algorithm which satisfies this? That's what I'm going to do next. Yes?
For the Q-noise case, if you replace, if A is like infinite, but has description length.
If A?
If the action space is
Yes.
infinite, but has some description.
Yes.
Say K.
Yes.
Does the complexity simplify? Like the log n is basically the number of bits you need to describe an element of the action space.
Very good, very good. So we will talk about that. That's another topic, which is, it goes into this, but we'll do it today. The answer is it's more complicated, but but we'll talk about that. Okay. All right. So now I will start with an algorithm, just a simple algorithm. So what is, by the way, the mathematical, the concept that we're trying to attack mathematically in the full information game? It's the concept of hedging. Okay, what you really want to do is that you have some information. Right now, you believe some action is the best. You could put all your money there and play that action, but this wouldn't be smart because you know that there is an adversary, or at the very least, you cannot make any assumption about the environment. So maybe tomorrow, what was the best, yesterday is going to be the worst. Okay, so you have to hedge a little bit. You have to say, okay, yes, this has been performing very well, so I want to put a lot of money there, but I still want to disperse a little bit of my money on other assets. Okay, this is just, I hope you guys are all doing this. Okay, so here is an algorithm. So multiplicative weight. So this idea has been rediscovered in many, many communities throughout time, and I will attribute it, I will not attribute it, but I will just give some references in the ML community. So Vovk in the 90s, Freund and Shapiri in 96, and what's his name? It's Warmos, but who is the guy who is with Warmos? Of course I didn't. What? Littlestone, okay. Little Stone and Warmouth. Okay, so this is just in my community, but again, it has been rediscovered many times. And the idea goes like this. So let's simplify. We put ourselves. This is just to give you the key idea, okay, in the simplest setting. So let's say we have an oblivious adversary, and let's say that the losses take value in 0 or 1. Okay, so assume oblivious and LIT is going to be in 0, 1. Okay, so I write it LIT. I keep changing my notation. I'm sorry about that. So LT of I is the same thing as LIT. Okay. Sorry, and I meant in the set 0 or 1. So really, you can think that at every time step, the actions are really trying to make prediction, and either they are correct, in which case they get 0 loss, or they are wrong, in which case they get a loss of 1. And what the algorithm does is that it's going to keep a weight for each action. And if the action mispredict, if it had a loss, okay, it didn't predict correctly, then we just decrease multiplicatively the weight. Okay, so idea. Keep a weight, WIT in R plus for each action. So right now we are in full information, right? And the update is going to be like this. So upon observing the loss, okay, so how did each action perform, you just set at time t plus 1. So it's going to be 1 minus eta LIT times WIT. Okay, so if LIT is 0, then we just keep the weight the same. If LIT is 1, then we shrink the weight by 1 minus eta. Okay, so we just shrink the weight of everybody who mispredicts. And how do we play? Play from just the normalized weight, from PT, which is equal to WT over the L1 norm of WT. Okay, so that's what we play from. That's how we're going to hedge. That's the algorithm. What is the key intuition? And this is really the intuition, that encompasses everything. I mean, the reason why you can do something at all. So the reason is as follows. Say I star is correct at round t. Okay, consider a round where the optimal action is actually predicting correctly. Then we are learning. Then we are learning because you see the weight of I star is not going to shrink, but the weight of some other action is going to shrink. Okay? So we do get closer to I star. Okay? Then W I star t remains constant, and others shrink. So what does it mean? It means that PT plus 1 is closer to a point mass at I star. Okay, you can think of this as this distribution, right? Think of the unnormalized distribution. So I don't normalize to have weight 1. Then what I did is that I just shrunk, many guys, or a big fraction of them. But the best one, I didn't shrink it. Okay, so this guy, it remained constant. So I'm becoming more picky. I'm getting closer, to a point mass at I star. And on the other hand, if I star mispredict, then we're fine because I star paid. So indeed, maybe we get confused. Maybe we do not get closer to a point mass at I star, but the optimum had to pay for it. So either we get closer, or if we didn't get closer, then there is a reason for it, which is that I star had to pay. Okay, so this is really the key intuition. Okay, and the theorem that we're going to prove is the following. If I look at my loss, then this is going to be bounded by 1 plus eta times the loss of the optimum plus log n over eta. Okay, so here I write it not in terms of a regret bound. So this type of bound is also interesting. So this type of bound is more multiplicative. So what I'm saying is that my loss is very close to the loss of the optimum. Okay, it's 1 plus eta. Think of eta as being some small constant. So it's 1 plus eta times L star up to an additive term, which is log n over eta. Okay. So if I optimize over eta, so if you optimize over eta, then you find that your regret, okay, I just put L star t here. I get eta L star t plus log n over eta, so I get the harmonic mean, the geometric mean, sorry. You get square root L star t log n. Okay, maybe with a factor 2. Okay, that's what I get. Which is, of course, you know, if I just wanted, I could write it as square root 2 t log n. Okay, so we see this bound that I mentioned, which we're going to show is a pure noise bound, but we also show that it satisfies this easy data bound. Okay, that if the loss of the best action is small, then we get a better regret. And the proof is going to be simple, but at this point magical, and we will demystify it this afternoon. So the proof is very smart. So it's a potential-based analysis. Or Lyapunov function argument. And what is the potential? The potential is just going to be the L1 norm of the weights. Okay, so let's look at how the L1 norm of the weight evolves. Okay, the sum of the WIT plus 1. What is it? Well, I have this formula. Okay, so this is the sum of 1 minus eta LIT WIT for I equals 1 to n. Of course, I want to relate this to the potential at the previous time. I mean, that's how the potential-based argument works. So let's introduce the L1 norm of W. So I get that this is equal to the L1 norm of WT. Okay, now I divide this term by the L1 norm. So now what is this? This is PIT. Okay, I get the sum of PIT, which is 1. And here I get eta LIT PIT. So this, I will write it as 1 minus eta inner product PTLT. Okay, so this is my notation. PL is just the sum over I of PI LI. Okay, this is just the inner product in Rn. I use this notation because I think of testing L against a measure P, and when I have just a general point in Rn, I will write x dot L. Okay, it doesn't matter, it's the same thing. And notice that LT, the loss of the player, the expected loss is nothing but the sum, you know, in expectation, the sum of PT LT. Let's say without the expectation. Right? I play at time step t, I play IT at random from PT. So in expectation, what I lose is the sum of PTI, LTI. Right? And there is no expectation because we are in the oblivious setting where the losses are independent of the player. Okay? Very good. Now what do I want to say? Now I want just to use that log 1 plus x is smaller than x, okay? Or 1 plus x is smaller than e to the x. So 1 minus this is smaller than e to the minus this. Why do I do that? Because I will have an induction, right, and I get a product. So this is smaller than the L1 norm times e to the minus eta PTLT. Right? This is just using log 1 plus x is smaller than x. But now I'm in good shape because this, by induction, it's smaller than this term with a t minus 1 times wt minus 1. So I can just, expand the product. And what I will get is that this is equal to the term at the beginning. What is the term at the beginning? At the beginning, of course, I didn't say it, but you initialize the weight to be 1 for everyone. So all the weights are 1. So the L1 norm at the beginning is n. So what I find is n times the product for t equals 1 to capital T of e to the minus eta ptlt. And this product, right, it's exponential of the sum. So this is n times e to the minus eta capital LT. So you see that as I'm losing, the weights are shrinking. Which one? Is this one? This one, so you see, just you can see it by induction, because at the first step, oh, I see. Yes, it's an inequality. Yes, thank you. Sorry. Yes, it's an inequality. Yeah. Any other question? So you see that the weight is shrinking at a rate which depends on how much I'm losing, but the weights are also lower bounded. Why are they lower bounded? Well, just look at the weight of the optimal guy. The weight of the optimal guy is shrinking every time the optimal guy is making a mistake. So the weight of the optimal guy is just 1 minus eta to the power of the number of mistakes it made. Okay? But, so on note, Wi star at time, let's say, t plus 1, this is nothing but 1 minus, or maybe just I, for any I, this is 1 minus eta to the lit. Okay, and lit, my definition of lit is just the sum of a point mass at I times lt. Okay, so just every time an action makes a mistake, its weight shrinks by 1, and it starts at 1. Okay? And, yeah, good. So what do we see? We see that this thing is lower bounded by that. Okay, so we see that 1 minus eta, let's say, times L star t is lower bounded by n e to the minus eta lt. Okay, so I can now just take the log, and what do I find? I put this on the other side, so I find eta lt, let's say, minus log 1 over 1 minus eta times L star t. This is bounded by log n. Okay. I just took the log in this inequality. And we wrote, we like to work with positive quantities, so I just rewrote log 1 minus eta as minus log of 1 over 1 minus eta. What is this? Well, this is roughly, it's bounded, it's eta plus eta squared. Okay, I just have the first term and the second term. So what do I find? I find exactly eta times my regret plus eta squared times the opt is bounded by log n. Okay, so if I just rewrite this, I get LT. If I renormalize by eta, it's bounded by 1 plus eta L star t, LT, plus log n over eta. And maybe here I use something like eta, let's say, is in 0, 1/2 or something like that. Okay, just to get this bound to be valid. Okay, so you see the proof is very simple, but it's a bit magical, at least to me. I mean, we have this intuition, which is essentially written here, but we will see really a much cleaner way to do this using the mirror descent framework, which is a generalization of gradient descent. Okay. So now we're going to see what I believe to be a more principled approach to this problem, but maybe first the lower bound. So the lower bound. okay, in the pure noise scenario. So here is the theorem. For any algorithm, there exists a sequence L1 up to LT. Let's say in -1, 1 to the n. Okay, again, this doesn't matter. It will just be to simplify my proof. Such that the regret is at least square root 2t log n plus, let's say, times 1 plus little o of 1, and this is with respect to t and n. Yes? Yes. So this, I will not talk about this in this course, but I can tell you just the idea. So indeed, you need to know the value of LT star, but you can do what is called the doubling trick. So, assume that opt is going to pay at most 2. Let's play as if it was playing at most 2. Oh, now I'm paying 4. So probably L star was not 2. So now let me assume that L star was, whatever, 16. And, you can do like this, and because of the subadditivity of the square root, this will work. Yeah. The same thing for knowing the time horizon. The same trick. Any other question? Yes? If you what? If you know the regret, so you know how much effort you are doing, is it not more natural to weight the action by some decreasing function of the regret? I see. Yes. You recover the same complexity. Yeah. So I think what you're saying would improve the numerical constant in front of the regret. Yes, absolutely. Yeah, and people play those type of games. Okay, very good. So I want now to prove this lower bound, saying that you cannot do better than square root 2t log n up to a term which vanishes when t and n are big. So let's do the proof. The proof is using, if you wish, the probabilistic method. So I'm going to show to you a lower bound on the expected regret when I take losses at random according to a certain distribution. So if the expected regret with respect to random losses is big, that means that there is at least one realization of the losses such that it's big. Okay, so enough to lower bound the expected regret with random losses. Okay, I hope this is clear. I don't know who was the first one to use this type of argument, but Herder certainly made himself famous using this kind of technique. Okay, so what we're going to do is that we're just going to take it completely at random. Okay, let's take just uniform at random in -1, 1. Okay, either -1 or 1. So take LIT from a Rademacher. Okay, which just mean +1 with priority half and -1 with priority half. Okay, so in that case, so you just take, it's completely random. The past tells you nothing about the future. It's completely pure noise. And what is my expected loss as a player? There's nothing I can do. No matter how I hedge, in expectation, I get 0. So I always get 0. But what is I star? So I star can optimize. So I star, so the expectation of L star t, that's the expectation of the minimum over I in n of the sum of the LIT for t equals 1 to capital T. But by the central limit theorem, what this is going to be. Okay, what is these distributions? They have 0 mean and variance 1. So this, I expect it to be something like square root t times a Gaussian. Okay, up to some error term. But now what is the maximum of n Gaussian? The maximum of n Gaussian is of order square root 2 log n. Okay, just remember this. The expectation of the max of n Gaussian, of n01, this is equivalent when n goes to infinity to square root 2 log n. So the loss of every action is roughly square root t times the Gaussian. So the minimum or the maximum, let's say the maximum, would be square root 2 log n times square root t. So this is roughly square root 2t log n. I mean, it's equivalent to this when n and t goes to infinity. Okay, so in this pure noise scenario, there's just nothing you can do. This is the loss that you get. Yeah? Yes. Yes. Yes, 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 yes. So it's, yes, it's independent across time and across arms. It's just IID everywhere. Yeah. Okay, so now we're gonna see an information theoretic proof of this upper bound. Okay, so the same as the one we got with multiplicative weights, but it's gonna be completely principled. You won't need to be smart just to know a few things, like the Minimax theorem and the theory of type and cotype. Okay, maybe not everybody knows the theory of type and cotype, but it's a very natural thing, much more natural, I think, than multiplicative weights. Or at least than the proof that we showed. And we will even get the tight constant. Okay, here we didn't get the tight constant using this. So a more principled approach. So it's going to be game theoretic and information theoretic. Okay. So what are we after? Okay, what do we really care about? We care about the minimax regret. So what is the minimax regret? So let me write it like this. So let me generalize a little bit. So say player picks an action, let's call it AT in A, and adversary picks L1 up to LT in L. Okay, so the adversary, so I'm in this oblivious setting, where the adversary chooses at the beginning a loss function, and the player just picks an action in some set A. Okay, so it just generalizes a little bit what we were doing before. Now, what is a deterministic strategy? What is it really? Maybe let me write L to the T, just to clarify. So what is a deterministic strategy in the full information case? So in the full information case, really the action that you pick, it's an operator that maps the history to an action. Okay, so let me write A sub S, or maybe A sub T at time T. This maps L to the T minus 1 to A. Okay, so it takes as input a sequence of observation of T minus 1 losses, and it tells you an action to play. Okay, again, this is a deterministic strategy. In Bandit, A sub T, it goes from, let's say, 0, 1 to the T minus 1 to A. Okay, it takes a sequence of numbers, and it outputs an action. What is a randomized strategy? So maybe let me so denote a lower bar for the set of deterministic strategies. Okay. So yes. No. You do. So you do, but let me think. Maybe we don't need to say it because you see, it's a deterministic strategy. So I know what I would have played in the past. Yeah. So you don't need to specify it. You know, given this, I can simulate what happened in the previous time step. So this is general enough. Now, what is a randomized strategy? Okay, a randomized strategy, I described it previously, but in fact, with this notation, I claim that it's just a random deterministic strategy. Okay, so this is not totally obvious, but I don't want to get into this. So this is called Kuhn's theorem. But let me get away with this. It makes sense. A randomized strategy is just picking at random a deterministic strategy. If you wish, one way to think about it, and that's how the proof goes, is that a randomized strategy, every time step, I have to make coin flips. Now, in this view, in saying that I pick at random a deterministic strategy, I just make all the coin flips at the beginning. And it's basically the same, Whether I make the coin flips on 9 or at the beginning, it doesn't matter. Okay, you need some, assumptions on A, but it will all be satisfied for us. Okay, so now with this notation, and of course, when I write delta of a set, I just mean the set of measures, supported on this set. And I would, yeah? Say again? Yeah. So I just said briefly that there are some assumptions to be satisfied for everything that I'm going to say now, but they will all be satisfied in the application that we care about. And, since it's not the crucial part of the course, I don't want to focus too much on it. But yes, you're right. You're especially right because we're going to apply Sion's Minimax theorem in a minute, and then you really need it. Okay. So what do we care about? So what is the Minimax regret? So the Minimax regret, the quantity we care about is we want to find the best strategy. So we want to find the inf over mu in, randomized strategy, such that no matter what is the adversary, so the supremum over, let's say, L bar in L to the T of the expectation when I play a deterministic strategy from mu at random of the regret when I play A against L. Okay, so let me clarify the notation. So RT of A bar L bar, that's just the regret, if I play this deterministic strategy and the adversary plays this deterministic sequence of losses. So the way I want you to think about it is that I have this huge matrix, infinite matrix, where, for every row is a deterministic strategy for the player. Every column is a sequence of loss for the adversary. And the entry is just how much, what is the regret in that case. If the player plays this deterministic strategy and the adversary plays this sequence of losses. So this is just a big matrix. And now what I'm looking at is the infimum of the whole randomized strategy for the player, of the supremum of the whole loss function for the adversary, of the expected regret. So this is the quantity I care about. Now, of course, maximizing over this is the same thing, because this is a linear function, as maximizing over the set of measures. Okay, so this is equal to the inf over mu of the supremum over nu, which is a measure now over loss sequences. Okay, here I did nothing. The expectation over A bar is sampled from mu, and L bar is sampled from nu. Right? If you think in terms of those matrices, it's just here I'm finding the worst column. So certainly the value of the worst column is bigger than the value of the average of some average column with respect to any distribution. But I can also pick the distribution which is just the point mass on the worst column. Okay, so these two quantities are the same. And now the smart move is just to swap the inf and the sup. Okay, which you can do by Sion's minimax theorem. So let me remind you, Sion's minimax is the following. If you have x and y, let's say, let's say I have a phi from xy to r, which is convex. So phi dot y is convex, and phi x dot is concave. Okay, so phi is convex in the first argument and concave in the second argument, which is the case for us. For us, our capital X is going to be this set of measures. Our capital Y is going to be this set of measures. And our phi is going to be this function, which is just a bilinear function. It's linear in mu, and it's linear in nu. Okay? And then you need phi to be bicontinuous. Let's say X is compact. And then you can swap the inf and the sup. Then what you get is the sup, which is in fact max, the inf, sorry, inf over x in x of sup over y in y of phi of xy. This is equal to the sup inf of phi of xy. Sup over y in y, inf over x in x. Okay, this is the basis of game theory, and I'm sure many of you have seen it. Okay, so now we're just going to apply this to our problem, and in our problem, in fact, it's bilinear, and as I said, you can verify those compactness assumptions for the problems that we care about. And you will see that something quite nice happens once you do that. So now this thing is equal to the supremum over nu of the infimum over mu of this expected regret. But now let's interpret this. What this means is that now the adversary comes first. The adversary plays first. So the adversary picks a distribution of our loss functions, and me, as a player, I get to choose my strategy as a function of this distribution. So now you're in what's called a Bayesian setting. Okay, now you have a prior distribution over the sequence of losses. Okay, so this, once you have changed the order, this is a Bayesian setting. Okay. It's a Bayesian setting, yeah. So now, nu is a prior distribution on L1 up to LT. Of course, this is not a product distribution or anything like that. There is no IID assumption or anything like that. This could be, the worst case, the distribution that maximizes this thing. I have no idea what it is. It could be something very complicated. But the fact is that now, when I want to bound this, I can assume that I know this prior distribution. And as a good Bayesian, as you make observation, you will update your prior distribution. You will get some posterior distribution. Okay, and you will play from this. Now you have some information. So in particular, you know the distribution of I star. So I star is the optimum, the best action. It depends on this. It's a random variable which depends on this realization. But now you know its distribution. So in particular, we know the distribution I star. We know the distribution and we can update it. Okay. So, yes, please.
Why do you talk about updates? Don't we already know the full path of the rewards?
No, so you don't know the realization, you just know the distribution.
Okay, so
Yes, yeah, you just know the density, and as you play the game and you make observation, you can refine. So let me be more precise. Let me denote the expectation sub t. This is going to be the expectation when I condition on L1 up to LT minus 1. So at the beginning of time step t, I have made those right now we're in the full information setting, I have made those observations. Right? So I know, now I have this posterior distribution, and I will be able to make computation with respect to this. In particular, I can update the distribution of I star. Okay, so idea. I think a fairly natural idea once you see this. So there are many ways to come at it. So I star, let me view it as, again, I prefer to view it as a point mass in I star. You know, I think of, again, you're hedging, so you're playing probability measures. So really what you want is to get to a corner of the simplex. By convexity of the simplex, it's pretty natural to play the expectation of this guy. Okay, so idea, play PT, which is the expectation sub t of delta I star. Okay, so I think of it as a natural way, geometric way to combine, you know, the information. But this is also called, you can also view it as probability matching. What do I mean by this? So the probability that you play action I is exactly the probability that I star is equal to I given L1 up to LT minus 1. Okay? You just say, you know, right now, given my information, I know that, you know, this action is going to be the optimum with probability 1/3, and this action is going to be the optimum with probability 2/3. So my way of hedging is going to be, I play this one with probability 1/3, I play this one with probability 2/3. Okay? Or more geometrically, by convexity, this is a natural, you know, you have this, okay, you have this random variable and you're taking the Doob martingale. Okay, so this is a Doob martingale. You know, at the end, you want to get to this corner. You have this random variable and you're discovering more and more information about this random variable.
What is that in general, Doob martingale?
Sorry?
I know what is a martingale, but what is a Doob martingale?
Doob martingale just means, I mean, it's essentially any martingale, but what you do is that you have this natural filtration, and you just take the expectation of this random variable conditionally on this filtration. Okay, so you just discover more and more. You know, you zoom in if you want on this thing.
Kind of axiomatically defined martingale by
Yes.
with respect to the past. Okay.
Yes, exactly. Yes. Okay, so let's analyze this. So the analysis is really neat. I forgot to mention the references. So again, it's a bit difficult to track down with the first one. There is a paper by Abernathy and Warmus from, I think, 2008. There is a paper also by Sridharan and Terrari from 2010. And the approach that I'm presenting here, it's simplified with respect to this paper, and it's going a little bit beyond. So this was my work with Ofer Deckel, Tomer Koren, and Yuval Perez in 2015. Okay. But there are many other people who looked at this. Before our paper, somehow people were really focusing on the non-oblivious setting, which makes everything more complicated. But if you focus on the oblivious case, things are really simpler. OK, so the analysis goes like this. What do we care about? We care about the sum of PT minus delta I star LT for t equals 1 to capital T. And we want the expectation of this. Expectation with respect to the LT. Now, here is the beautiful identity. In this, when I calculate this expectation, I can condition on LT. If I condition on LT and everything before, what is the expectation of delta I star? It's PT plus 1. Right? Because PT plus 1 is the expectation with respect to everything, including the loss LT. So this expectation is equal to the expectation of the sum for t equals 1 to capital T of PT minus PT plus 1. Okay? And this is great because now I have essentially gotten rid of this delta I star, of this I'm only talking about the algorithm, in a sense. And now I will just use Hölder's inequality. So let's assume that this LT, the L infinity norm of the LT is bounded by 1. Okay, so LT can take value between minus 1 and 1. Then this thing is upper bounded by the expectation of the sum for t equals 1 to capital T of the L1 norm of PT minus PT plus 1. Right, you remember we're going to use this many, many times. The inner product between A and B, if I have some norm, it's smaller than the norm of A times the dual norm of B, by definition of the dual norm. And the dual norm of L1 is L infinity, or the dual norm of L infinity is L1. So we get this. So we get that our regret is bounded by the variation in the posterior. And now comes the geometry of martingales. Now you want to understand, you have this martingale, the geometric picture is like this. This is the simplex in high dimension. And you're going to end up at one of the corners. But what you're doing is that you're moving. This is maybe P1. Then you move somewhere. This is P2, etc. You keep moving like this in a martingale way. And eventually, you will concentrate over there. The question is, how much movement can you have until you get there? Or put another way, how stable is a martingale? And this is exactly the theory of martingale type and cotype is exactly getting at this question. If you have a martingale in a certain Banach space, which here is just L1, how much variation is there in your martingale? And what we'll see is that I will show to you a bound, which is a famous bound on this thing, which is essentially the type 2 bound for L1. And the proof, what it's doing is that, in fact, this martingale, when it moves, it consumes some entropy. So every movement is not free for the martingale. When the martingale wants to move, it's going to decrease its entropy, because eventually it has zero entropy. Eventually it gets to a point mass. So as you move, you decrease your entropy, and the proof of this variation bound is exactly going to be doing that. So that's what we're going to do now. And we'll see we get exactly the optimal regret. Okay, I will show to you a bound. So let me call it a famous inequality because I don't know to whom to attribute it. The famous inequality is going to be like this. The expectation of the sum of the L1 norm of the distance. So now PT could be any martingale, of the L1 norm squared. This is bounded by 2 log n. Okay, so again, we're going to prove this, but this is the bound. So the first time, certainly the first time I saw this, I was a bit surprised. I mean, you have this sum over t, but the right-hand side does not depend on t. But once you see the proof, it makes a lot of sense. It's just cannot keep moving a lot. At some point, it has to make smaller and smaller movements. It's a martingale. It can, at some point, basically what you have to think is that at some point it's going to get cornered, literally. It's going to get to a corner, and then it cannot make big movements because it has to have zero expectation. Every movement has to have zero expectation. So if you're in a corner, you cannot move very much. And you can see where this is going. You can see that the notion of corner is going to depend on the convex body that you have. So the simplex is going to give you certain rate, but other convex bodies will have properties of getting corner which are different. So that's what we're going to see also. Okay, so let me assume this now and finish the proof using this. So assuming this bound, what do we get? Okay, so we want to bound the sum of the L1 norm without the square. Okay, if you want to bring in the square, just use Cauchy-Schwarz. So if you use Cauchy-Schwarz, you get square root of t times the expectation of the sum of the L1 norm squared. Okay, sorry, I did two steps in one. I use Cauchy-Schwarz, right? So I get the square root of the number of things that I'm summing times the square of the terms. But the square of the term should really be the expectation of this squared. And then I use Jensen, right? The expectation of x, everything squared, is smaller than the expectation of x squared. Okay, so I just did those two things. And now I know that this is bounded by square root 2 log n. So this is square root 2 log n t. Which is actually exactly the optimal bound, up to the constant. I showed to you that if you are in the pure noise scenario, then you even get this 2. Okay, so we really do get the optimal thing. And I would argue that this is more principled. You get at this more naturally. Of course, thinking ahead a little bit to the Bandit scenario, you can already see that the Bandit case is going to be much harder. Because this type of identity is just not going to be true anymore. Okay, because LT is not going to be measurable with respect to the filtration. Your filtration in the Bandit case is going to be, the losses at the point that you played. So you don't know what would have been the loss at the other points. So it's not true that the expectation of delta I, you cannot condition on LT. Okay, so in the Bandit case, it will be much more subtle, and that's why I want to do the proof of this famous inequality, because what you will need to do is to actually modify this proof in the Bandit case. Okay, so let me just do some reminders of information theory. Okay, so the entropy of a probability distribution P is just minus the sum of Pi log Pi. Okay, so the interpretation is that if you have an IID source from P, this is the expected length of the optimal code. Okay, this is the smallest expected length for a code that you can get to code your source distribution P. What is the relative entropy? The relative entropy between P and Q, it's the sum for I equals 1 to n of Pi log Pi over Qi. You also know what is the interpretation of this. It's a regret interpretation. So here, you have a source which is IID from P, but you code it optimally as if it was from Q. And the relative entropy is how much you regret doing that. How much longer is your average code with respect to if you had coded optimally with respect to P. Right? The correct way to think about this is that this is minus the sum of Pi log Qi minus the entropy of P. Okay, so it's how much more you pay for thinking it was Q when really it was P. I will really use the information theoretic notation. It took me a long time to appreciate it, but it's actually useful. So let's say I have a random variable capital X, okay, whose distribution is P little x. And I condition on some random variable y, which has distribution P little y, and I have a joint distribution Pxy. Okay, so these things, they have some correlation. So the entropy of x given y, this is really the sum for I equals 1 to, no, let's say it's the sum over y of py of y times the entropy of p of x given y. Okay? So this is the average entropy of, when I code the source x, knowing what is y. Okay? And the mutual information is how much reduction there is when I do this compared to just coding x without having the information on y. So the mutual information with respect between x and y, this is equal to the entropy of x minus the entropy of x given y. Okay, so it's how useful is y in predicting x, if you wish. Okay. This is also equal to a certain notion of relative entropy. So this is also equal to the sum of the relative entropy, let's say sum over y of py of y. Okay, maybe I shouldn't put py of y, but okay, just py of the relative entropy of p of x given y with respect to px. Okay, so this is just a simple formula. You can just check it. It all type checks. So what does this mean? What is this relative entropy? So again, this is the truth. Yeah, this is the truth. P of x given y. So let's say I know what is the value of y. How much do I regret coding, for x and forgetting what was y? Okay, this is this relative entropy, and that's the expectation of this. You see, it exactly matches the description I was giving here, which is how much you regret. Okay, and this thing, the mutual information is symmetric. Okay, the mutual information between x and y is the mutual information between y and x. Okay, is there any question on this short thing? Let me just check that I told you everything I want. Yeah. Okay, and an important inequality, which is simple to verify, but very important, relating the L1 distance to the relative entropy, is a Pinsker inequality. Which tells you that 1/2 of the L1 norm between P and Q, this is bounded by square root of the relative entropy. Okay, this is the last thing that I need. Okay, so now equipped with this, let's prove the famous inequality. And let's call it star. Yeah, please.
So we'll say norm 1 on P minus Q, it's the distribution norm 1. So if those are continuous function, it's integral.
Yes, so all of this could be done in over continuous spaces, but to simplify, let's think only about discrete. And then, this is L1 norm.
Yeah, so just sum of terms.
Sum of terms, absolute value. Yeah, but otherwise you're right. Okay, well, so we have Pinsker, we have an L1 norm squared, so we can bound it by the relative entropy. Right? So the expectation of 1/2 the sum for t equals 1 to capital T of the distance between pt and pt plus 1 L1 squared. This is bounded by the expectation of the sum for t equals 1 to capital T of the relative entropy between, let's put pt plus 1 first, and pt. Okay. And let's try to clarify a little bit what we're doing. This is a random variable. Right? pt plus 1, this is the expectation at time t plus 1 of delta I star. And this is the expectation at time t of delta I star. Okay. So again, this is the probability distribution of the opt, okay, given all the information up to time t. and this is the probability distribution of the opt up to time t plus 1. So really what this is the same distribution as this plus some information. It's the same random variable plus the information of time t plus 1. So you can see it's going to be a relative entropy of this form. Okay? So this term, in fact, is going to be a mutual information. So let's see that. So the expectation with respect to conditionally on everything up to time t of the relative entropy between pt plus 1 and pt. This, if you want, so let me write, let's see, let me write p I star t. This is this thing. Okay, so what I mean by this is the distribution is the probability distribution of this random variable I star when I have condition on everything up to time t. Okay, so this is the sum. Okay, how do I want to write this? This is the expectation up to time t of the relative entropy between p I star at time t, but also given Lt with respect to pt. And this expectation is, of course, with respect to Lt. So this is exactly a mutual information. This is exactly this formula. So this is equal to the mutual information, where by mutual information, I think that I have conditioned everything up to time t. Okay, so all my measures, the only randomness is for LT, LT plus 1, etc. So this is the mutual information at time t between the optimum and LT, which is a quantity which makes a lot of sense, which we like. You know, it's how much information the current round is giving us about I star, given everything that I already know. Okay, so it's a very good quantity. Yes? Yeah, let me see if I made something incorrect. So yeah, so I think it's good. So E sub t has everything up to the start of time t, so it has everything up to t minus 1. It has L1, L2 up to Lt minus 1. Yeah. Thanks. Okay, but now what do I want at the end? You know, I have this sum over t terms, and I want something independent of t. A good way to get that is to have a telescopic sum. So, and we'll get this because what is this mutual information? It's a difference of entropies. Okay, so this is equal to the entropy at time t of I star minus the entropy at time t plus 1, minus the entropy, minus the entropy at time t of I star given Lt. But what is the entropy at time t of I star given Lt? This is nothing but, this is equal to the expectation sub t of the entropy at time t plus 1 of I star. You see, this term, by definition, the entropy of I star given Lt is nothing but the entropy of I star, but conditioned on everything up to time t plus 1. So what I see is that this term that I'm summing, it's in fact a difference of entropy. It's just how much did the entropy get reduced by observing Lt. Okay, so I get now a telescopic sum, and the only term that's left is the entropy at the beginning. So now, so this implies that the expectation, you know, of what we cared about, the sum of the L1 norm squared, this is upper bounded by simply the entropy at time 1 of I star. So how much randomness, how much entropy is there in this random variable, you know, whose double martingale I'm taking, how much entropy is there? That's the bound. Particularly, it means that really the regret bound here, I could replace this log n by the entropy of I star, which maybe can be better, you know, in some cases. So the first one to observe this is Russo and Van Roy in a really, really nice paper in 2014. So they gave this bound of square root 2t entropy of I star. Okay, and they didn't know about type and cotype, so they just reproved this bound. But that's all they are doing. Okay, so this is just a finer, again, it's like an easy data, if you wish, bound. But this is an easy data bound if you think in terms of Bayesian setting, but if you think in the term of the Minimax setting, then it's just doesn't improve. Okay, is there any question before I move to the Bandit case? Yes, please.
Inequality, there is something that bothers me.
Yes.
At the left, we have something which is symmetric.
Yes.
And at the right, we have something.
Yes. 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 So it's symmetric, but you have to be a little bit careful. There is time. I mean, time has a direction. So yes, you're right. This quantity is symmetric, but there is an order. I mean, pt plus 1, it's nothing but pt with more conditioning. So I agree. You're saying here you could invert pt and pt plus 1.
Even in the inequality.
Yeah. Yes. Yeah. Here there is a choice to be made when you apply Pinsker. You have to make a choice. But here there is a choice, a natural choice. Because what you want to put on the left-hand side is the truth. Because in this interpretation, the left-hand side is what is really the true source of your data. Now, what is the true source of your data? The true source is if you knew in advance L1 up to L capital T. So the more you condition, the closer you are to the truth. So it's more natural to put pt plus 1 on the left-hand side. Okay, so let me just make a quick comment, but I don't have time, I think, to do it in details. It's a more general story of type and cotype. So, more general story. Do I want to do that now? Okay, maybe let's take a 5 minutes break, and then I can think what I do next. So we start again at 11:45. Okay, so I think it's better to not talk too much more about type and cotype for now. I will maybe mention it a little bit later, but now it seems more natural to me to move to the Bandit setting and get a bound for the Bandit setting. Okay. So now we'll do the Bandit analysis. I don't remember which number we're at. Doesn't really matter, but I think it's 5. And this should really be attributed to this very nice paper by Rousseau and Van Roy. As I said, in the full information game, they just reproved the cotype 2 of L1, but for Bandit, you really have to do something different, and that's what those guys did. So let me explain. So let me remind you what we did before. So in full information, we had the following very nice inequality. Pt minus, let's say, delta I star, Lt. This in expectation was equal to the expectation of the sum of pt minus pt plus 1 times Lt. And the reason why this was true is because we were conditioning here on Lt, and condition on Lt, and condition on everything up to time t, the expectation of delta I star is pt plus 1. But now in Bandit, this is not true anymore. The filtration, the Bandit filtration, F is the expectation sub t. You are integrating with respect to I1, L1 of I1, etc., up to IT minus 1, LT minus 1 of IT minus 1. Okay, so you have a much smaller filtration. Okay, so because you have a smaller filtration, you can imagine that your martingale will be able to move more, in a sense, which is what's going to happen. But in particular, this inequality now this equality is not true in Bandit. Okay, you cannot do that. But still, you know, it doesn't mean, it's not because this equality is not true that the final bound is not true. Okay, so what is our hope? Our hope is that maybe, so hope is maybe, so let me give a name to this. This is going to be, let me put a sum outside, and the expectation for what is inside, up sub t, like this. Let me call this R sub t. So this is my instantaneous regret. This is how much I regret at time t for playing from pt compared to playing from delta I star. So maybe we can hope to prove that R sub t is upper bounded by the expectation sub t of pt minus pt plus 1. Okay, and again, in the full information, it was just true because in expectation this was equal to this, and then you just applied Hölder's inequality. Okay, let's try to think about what this means. This means that I have some variation in my posterior. My posterior is actually changing. I obtained some information about I star, and the more I regret, the more information I obtain. Okay, the more I regret, the more information I obtain. Now, in full information, the information comes at you just for free. But in Bandit, really a crucial part is the learning aspect. You have to, you know, willingly explore and take some actions that maybe you wouldn't take, you know, given the information that you currently have, but you want to take it because you want to get more information. So you have to change something, at least in the analysis. Okay. So we won't be able to prove this. But what we will be able to prove is a weaker inequality, which is sufficient given, you know, how do we apply this? How do we apply this is that after that we apply Pinsker inequality. Right? So we get that this is bounded by square root of the relative entropy, which is a mutual information term. So a weaker inequality that suffices given what we have talked about, weaker inequality that would suffice. Is that RT should be bounded by square root of the mutual information, given everything that I have up to time t, between opt and my information right now, which is IT, LT of IT. Okay, so this is a weaker inequality than this, because by I can apply Pinsker inequality and do what I did before, and I would end up with this. And it's all we need. Okay? And the same story applies. This is, again, a notion of information, and you want to say that if you regret, then you learn something. You have some information. Okay? So let's try to prove this. And now, let's try to prove this without modifying the strategy. So this is a little bit mind-blowing, and it's called Thomson sampling. So it goes back to the very first paper on bandits from 1933. So I didn't mention it at the beginning of the first beginning of the talk, but the origin of bandit theory is for medical trials. So you imagine, instead of users coming on a website, you have patients coming to a doctor, and they are sick, and you have, n different treatments, and you can choose which treatment to give, and then you just see whether you cure the patient or not. And as patient comes, you want to cure as many as possible. So Thomson was interested in this, and what he was doing at the time, it made a lot of sense, and it still does today, is that he worked in a Bayesian setting. So he had some prior distribution over which treatment went better than other, etc. And as patients were coming and he was giving treatment, he would update the posterior and then play just the probability matching. Okay, so just play, given the information that I have, I believe this treatment is going to be the best with priority 1/3, this one with priority 2/3. So let me give that one with priority 1/3 and this one with priority 2/3, which is exactly what we're doing right now. Okay, but in the Bandit setting, it makes sense to call it Thomson sampling. And now it's really important, this sampling part. Okay? Before, in full information, the sampling didn't matter. The only thing we were doing is we were just saying LT of IT in expectation is the inner product between PT and LT, and that's it. Now we can forget about IT. But now here, IT is really, really important. This is the exploration part. Okay, I also didn't mention those words, but the basic tension of Bandit is between exploration and exploitation. Okay, maybe given your information right now, you really would like to play this action. You believe that you will have a smaller loss, but it makes sense for future reward to play some other action. Maybe you want to explore more and exploit later. Okay? And Thomson sampling does this trade-off automatically. Maybe what do I want to keep? Maybe I will keep this. Maybe I will move here. Okay, so let's try to prove this new inequality, which we're going to call double star. Okay, so to prove double star, to hope to prove double star, let's try to rewrite what is our regret, instantaneous regret, and what is the mutual information. So some notation. So let me denote L bar T of I. This is the expectation sub T of LTI. And L bar T ij. This is the expectation sub T of LTI given I star is equal to J. Okay? So one way to think about this is that I'm going to play some action I. I'm going to observe. Now you really have to think about the randomness in the observation. In this randomness in the observation, there could be some noise which is irrelevant to determine what is the optimal value at the end. What you want is to remove this noise and only care about the variability which has to do with the optimum at the end. So this is what this is doing. It's saying, if I star was this point, what is the variability left in the observation that I make? Okay, so this is a key quantity. Now, what is our regret, RT, right, which is the expectation sub T of PT minus delta I star LT. So this is where the probability matching is going to be very good. PT, this is also the probability distribution of I star given the information that I have so far. So what is this? This is just the sum for I equals 1 to n. Okay, I have PTI minus something. So I have PTI times L bar TI. Right? This is the expectation given all the information that I have up to time t. So this is this part, PT against LT. Now what is the expectation? Sorry. What is the expectation of delta I star against LT? Well, I just have to draw at random what is the value of I star. Okay, drawing I star at random is just drawing it from PT. Now, given that I star is equal to I, what is the expected value of LT? Well, it's LT bar II. So this is just minus LT bar II with those notations. Okay, so this is my regret. My regret is the sum of PTI, difference between L bar TI and L bar TII. What is my mutual information? Mutual information between I star and IT, LTIT. Okay, so that's the next thing that I want to compute. So notice that before this mutual information, I was writing it in terms of I star, in terms of the entropy of I star. But now, as I said, the focus should be on your observation. This is really the focus of Bandit, is what do you observe? What is the data that you actually collect? So it makes more sense in the Bandit case to not talk about the entropy of I star given this, but to talk about the entropy of the observation given I star. Okay, so let me just see, I want to do it well. Okay, yeah. So this is nothing but, by definition, the entropy of the couple IT, LT of IT, minus the entropy of IT, LT of IT, given I star. This is a definition of the mutual information. And really, I should write HT, right? Sorry, this is HT. This is the entropies when I condition on everything up to time t, L1 up to LT minus 1. Now, I want to get rid of this IT. Okay, that's easy to do. Remember that just the entropy, the more I condition, the smaller the entropy. Why is this? Well, it's easy to see that the relative entropy is always non-negative. So the mutual information is always non-negative. So h of x is always bigger than h of x given y. So if I condition, I just reduce the entropy. So this is bigger than the mutual than the entropy of LT of IT given IT minus the entropy of LT of IT given I star and IT. Okay? Which is nothing but the sum. So now I just take a realization. So the sum for I equals 1 to n of PT of I. Okay, so I take a realization of IT, and now I get the entropy of LT of I minus the entropy of LT of I given I star. Okay, or to put it differently, this is the mutual information between LTI and I star. Okay, sorry, this was maybe a bit too pedantic somehow. I mean, it's maybe you see it clearly that the mutual information between those two things is just larger than I take this guy at random and I look at the mutual information between what's left. Okay, this is just a formal proof of this. Okay, so now let me continue my rewriting of those things. So what is this? So this is equal to just the sum of PTI of the relative entropy between LTI given I star. So LTI given I star and LTI. Okay, and really what I should write is this is, what is this notation? I just mean I star given I star is equal to j times the probability that I star is equal to j, which is PTJ. So this is PTI, PTJ. I have sum over ij. Right? Again, what am I saying? I'm just saying the mutual information between LTI and I star. Okay, it's the relative entropy when I take I star at random and I look at the distribution of LTI given the realization of I star and the distribution of LTI without this realization. Okay? So here, I'm sorry, it's just nice in information theory to confuse, you know, the random variable, the law of the random variable. But I hope it's somewhat clear. Okay. And now the last step that I want to say is that this relative entropy, this is bigger than LT bar I minus L bar T ij squared. Okay, and this step is Pinsker inequality. So why is that? Why is this Pinsker inequality? Okay, so the way you have to plus, this is Pinsker plus LTI is in minus 1, 1. Okay. So what is L bar Ti? What is L bar Ti? L bar Ti is nothing but I integrate this random variable against this measure. Okay? And L bar Tij is I integrate this random variable, But again, the measure where I have always also condition on I star equals to j. So in particular, this thing is smaller than the total variation distance between the distribution of LTI, and the distribution of LTI given that I star is equal to j. Okay, so here there are two steps. The first step is that you say, you use the definition that the L1 distance between measure is also a total variation distance. So the distance between the expectation of this random variable against a certain measure and the expectation of this random variable against another measure, this is smaller than the total variation distance between those measures, provided by that the random variable is bounded. And now the total variation distance is an L1 norm, and you get an L1 norm squared because I have a square here, so it's bounded by the relative entropy. Okay, so what we just proved, what we just proved is that the mutual information between I star and IT LTIT, this is lower bounded by the sum over ij of PTI, PTJ times L bar Ti minus L bar T ij. Okay, so this is what we prove right now. And what is our goal again? And we also proved that the regret is this. Okay, so the regret is just the sum over, if you wish, some kind of diagonal term, and this is the sum over all the term in a certain matrix. But you want to bound this by the square root of that. So you can see, again, you're just going to apply Cauchy-Schwarz and do something. Okay. So the conclusion is going to be like this. So now, what do? You do the sum of PTI, L bar Ti minus L bar Tii squared. No squared? Not squared. This is bounded by, okay, for I equals 1 to n, it's bounded by square root of n times the sum of the square of those terms. PTI squared, L bar Ti minus L bar Tii squared. Okay. Which is bounded, by the sum, if I sum over ij of PTI, PTJ, L bar T, blah, blah, blah. So it's bounded by square root of n times the sum over ij of PTI, PTJ, L bar Ti minus L bar T ij squared. Yes?
How do you mean the square here?
Say again? There is a square. There is a square. Yes. Yes, there is a square. Yeah. There is a square because I need the square to apply Pinsker.
But here no square. You can just take like one.
Here, there is a square. There is a square because this, think of that I have a matrix with entries PTI, PTJ, L bar Ti, L bar T, ij. No, here I have no square. Yeah, here I have no square, but I get a square when I apply Cauchy-Schwarz. Okay, so this is bounded by square root of n times the mutual information by what we proved between I star and IT LTIT. So again, this thing is just the difference between the entropy of I star at time t and the entropy of I star at time t plus 1. Okay? And so you can apply the same reasoning as before, and you get a telescopic sum, and the theorem becomes that your regret, the minimax regret, so the inf sup, is bounded by 2 times square root t n log n. Okay, so you get this extra n. You get this extra n because of this part of the random. And it just makes a lot of sense. Again, you don't expect your regret to be non-trivial when t is smaller than n, when you have seen less than all the actions. There's just no way. We'll see that, in fact, this log n is suboptimal and you can remove it, but I don't understand this from the information theoretic perspective. I don't know if there is a way to understand it from the information theoretic perspective, but we'll see an algorithm that removes the log n. It's also optimal, so just the lower bound is very easy, just the lower bound idea. So it's not exactly pure noise now. Imagine that you have one is, let's say, a Bernoulli 1/2 plus epsilon, and others are Bernoulli 1/2. Okay, by this I mean, imagine that the losses are IID across time and across arms. And when I say arms, I mean action. So one action is, let's say, minus epsilon. One action is a little bit better than the other. It has a loss on average smaller by epsilon than the other. So how many samples do I need to identify this? Okay, so I need of order of 1 over epsilon squared samples per arm. So I need 1 over epsilon squared sample per arm to identify, which one is the guy with 1 minus epsilon, 1/2 minus epsilon. So if I take 1 over epsilon squared equals n times t. Okay. What am I saying? Is that what I want? Probably not. T over n. So if I play for capital T steps, then on average, a fixed arm will have T over n, observations. I have capital T observation in total, so per action I have T over n observation. So if I take 1 over epsilon squared to be roughly T over n, basically at the end of the T rounds, I still don't know who is the best. But what is my regret? The regret is that every time step, I play an action at random, so roughly I get a regret of epsilon t. So it's roughly epsilon t, which is what? So epsilon is square root n t, square root n over t, so this is square root n t. Okay. So again, if I fix this value of epsilon such that 1 over epsilon squared is t over n, then by the end of t time step, I just did not observe enough samples to tell which is the action which has a mean 1/2 minus epsilon. And what did I pay at every time step? On average, I pay epsilon. I pick an action at random. The best I can do right now is I pick an action at random. Of course, to prove this, you have to say the best you can do is to pick an action at random. But you can think if you're trying to be to do anything clever, I will exploit you. If you're trying to bias things towards playing action 1, well, okay, I will hide the 1/2 minus epsilon with more chances on action 2 or something. Okay? So the proof is easy, but it's just, to me, technicalities. It's not, there's nothing really interesting going on. But did this make sense, just the idea? Right? Why do you need 1 over epsilon squared samples between those two things? It's exactly because the relative entropy between those things is epsilon squared. Okay, and you need basically the relative entropy. It tensorizes. So if I have t samples, then I will get t times. Okay, so the relative entropy between mu to the t and nu to the t. This is like t times the relative entropy between mu and nu. Once you get a relative entropy which is of order a constant, you can tell, you can find whether you get a sample from mu or nu. And I just said that the relative entropy between a Bernoulli of parameter 1/2 minus epsilon and a Bernoulli of parameter 1/2, this is essentially epsilon squared. So you need t times epsilon squared to be of order a constant, so you need t to be of order 1 over epsilon squared. That's the number of samples. Okay, anyways, this is basic statistics. I don't want to talk too much about this. But this tells you that this is the best you can hope for up to this log n term, which we will be able to remove. Okay. So now, just to motivate what I will do this afternoon, I want to briefly talk about a larger action set. So when you have many, many actions, but they are related somehow. And just see that the information theoretic bound gives us something. So I don't know if it's 6. Let's say primer on Bandit linear optimization. So now I'm going to assume that I have an action set A, which is a subset of Rn. Okay, and A is going to be discrete for now. It's going to be A1, A2, up to A size of A. Okay, so the way you should think about it is, let's say I'm trying, I have my website, I have a bunch of ads, and I want to decide which ad do I put, but my ads, I have feature for them. So I know that, an ad for a bike and for a car, it's more similar than if it was, I don't know, an ad for a drug. Okay, so I have some feature vectors that describe the ads, and when a user comes, its loss function is going to be a function of the correlation between this feature description of the ad and the user. Okay, so the loss LT, this is an element of Rn, and the loss for playing AIT is the inner product AIT dot LT. Okay, so now I have capital A action, but they live in n space. Okay, and this is my loss. And the normalization is assume AI.lt is always smaller than 1. Okay, so this is Bandit linear optimization with a discrete action set. Okay, again, my actions now, they are embedded in n space. Okay, I might have many, many, many actions, but they live in an n-dimensional space. And when the adversary plays a loss function, what he plays is something which is going to the value of my loss is how this correlates with the feature vector. Okay, so if I have these two actions, an ad for a car and an ad for a bike, if the ad for the car has a large loss, then I know that the ad for the bike also has a large loss because the correlation between those two things is large. Okay. Now the question is, can you exploit this correlation? Given that you see this thing, now you want to say, okay, I get information not only for this action that I played, but also for all the guys which are correlated with this action. So you want to propagate information. So this will be, the main focus of lectures 3 and 4 is how do you propagate information. Right now, we don't even understand algorithmically how to solve the finite-armed bandit case, so this will be for the afternoon. But let's see that this propagation of information is, in fact, automatically done again by Thompson sampling. So let me state the theorem. So naively, we would expect a regret like square root t times the size of A. Okay, but this is terrible. Now the theorem that I will show to you is that the inf soup of the regret, this is bounded by, and let me use bound with a squiggly to say up to a constant. I don't want to worry about constants, by square root t n log of the size of A. Okay, so this is much, much, much better. You see, the size only enters in a log. So you can really deal with something exponentially large. But of course, you pay the dimension. Why do you pay the dimension? Well, this makes sense. In full information, I wouldn't have this n. I would have square root t log of the size of A, because I compete with, a set of size of A. But now, what is my loss of information? My loss of information is, instead of observing n real numbers, I observe one real number. So I can expect a loss of 1 over n, okay, which is exactly what's happening here. Okay, so basically this is the best you can hope for, and it is attained. So it's really nice. I mean, it's really nice. And moreover, this is going to be when I swap the inf and the sup, this is achieved with Thompson sampling. Yes, please. Yes, yes. So this is, yes. So we will mainly talk about infinite A's. And for instance, even in full information, you know, what happens if A is infinite? So let me just answer your question before I do the proof. So we won't, I think I won't have time to do it, so let me just say the theorem. So it's just an aside. If A is infinite, but let's say the way we measure the complexity is in terms of some norm, but included in, let's say, the set of points x in Rn, such that the norm of x is smaller than 1. Okay, so you have some norm which measures the complexity. You know, maybe this A is a Euclidean ball, or maybe it's an LP ball, okay, an L infinity ball. Then what is the regret? Then the theorem, and I will leave it as an exercise, is that the inf sup of the expected regret is theta of t to the 1 minus 1 over q, where q is the cotype of the Banach space, which is Rn equipped with this norm. Okay, so I won't define what is cotype. Just it's a geometric, you know, it's a geometric parameter associated with a norm, and it's very, very closely related to this famous inequality that I wrote before. It tells you how the variation of a martingale is bounded in this space, where you measure the variation with respect to this norm. And what is Q? Before we were looking at the L2 norm of this variation. Now, if you have cotype Q, you have to look at the LQ norm of this variation. And you see that cotype is the right answer because you get it both for the upper bound and for the lower bound. Okay, it's a simple argument. It's very nice, I find it. Okay, so this is one possible answer to what you were saying, and we'll see other examples. I mean, again, the end goal of the lectures is to go to Bandit convex optimization, where you just have a continuous set and the adversary is playing convex functions. Here, the adversary is playing linear functions. Okay, so let me conclude this lecture by showing this theorem, by proving this theorem. And it's just going to be a slightly smarter upper bound than Cauchy-Schwarz. Okay, so the proof. Okay, proof of this. Maybe let me use a different. So I can do, you know, I can do everything I did before. It's the same setting than before, except that I have, you know, many actions and they are related to each other. So I can apply, you know, the same framework as before, and I will end up, you know, with my regret is this, except that instead of summing over n action, I'm solving over a actions. Okay. So here I certainly don't want to apply Cauchy-Schwarz. Okay, because otherwise if I apply Cauchy-Schwarz, here I get size of a. So I want to do something more refined than applying Cauchy-Schwarz. Yes, that's what I want to do. Okay, so let's do that. So how do I do something smarter than Cauchy-Schwarz? Well, I have to use the fact that there are correlations between this LTIJ, you know, for different values of j. So let me write. So what was L bar Ti? This was just the expectation sub t of LT of I, which by definition I'm going to say it's L bar T inner product with AI. Right? This expectation LTI, by definition, it's LT inner product with AI. So let me just call L bar T, which is the expectation of this vector conditionally on everything I have observed. And L bar T, similarly, L bar T ij, by definition, I say that this is the inner product between L bar T j and AI. Okay? So you see here, you can smell it. What I'm doing is I'm doing some kind of matrix factorization. I had this big matrix ij, and entry ij and entry ij plus 1 or I plus 1j, they were telling me nothing with respect to each other, but now I see that this is like a low rank decomposition. So let me be more precise. So let Mij, this is this matrix with those entries. This is a matrix with entry Pti, Ptj, L bar T minus L bar Tj, inner product with AI. Okay, this is my matrix, Mij. It's of size R to the A times A. Okay, it's a huge matrix. Now, what do I care about? I care about this quantity. Okay. What am I saying? Sorry, I'm just confused on something. What am I saying? Yeah, sorry. Yes, that's what I'm confused by. Square root of this. Okay. So what do I care about? I care about this term, which is nothing but the trace of M. You see, this is just the sum of the diagonal term. Okay, it's when I is equal to j, then this square root is just Pti, and this L bar T I. Okay, so this is the trace of M. Now, what is my mutual information? The mutual information is the sum of the square of the entries. So the mutual information is the Frobenius norm of M. Frobenius norm squared. Okay, so now I want to relate the trace of this matrix to its Frobenius norm. And what do I know? I just told you this is a low rank decomposition. So I know that this is of small rank. Okay, so in general, what we have is always the trace of M. It's just the sum of the eigenvalues of M, which by Cauchy-Schwarz is bounded by square root of the rank, the number of non-zero lambdas in this sum, times the sum of the square, the sum of the lambda I squared of M. But the sum of the square of the eigenvalue is nothing but the Frobenius square. The Frobenius norm squared, right? Because this is rotationally invariant. That's the whole point. So this is smaller. This is equal to the rank of M times the Frobenius norm. Frobenius norm of M squared. So you see that my smarter Cauchy-Schwarz, what it's doing is that it's replacing the size of this matrix by the rank. So now this, instead of N, I get the rank of M. But the rank is smaller than the dimension because I just provided to you, a factorization. This, I just wrote to you that M is equal to AB, where A, it's a matrix whose rows are, let's say, AI transpose. That's the row. And B, it's the column are up to the normalization, let's say, square root PTI. And B, the columns, so this is row, and this is columns, and here the column is L bar T minus L bar Tj, up to the square root Ptj. Okay, so in which dimension this lives? Okay, this has A rows, but only N columns. And similarly, this has N rows and size of A columns. So you see, I provided to you a decomposition of this matrix showing that the rank is N. Okay, so the rank of M is bounded by N. So when I do my argument, I will get an N here again. And now I have this telescopic sum of entropies. So what I'm left with is just the entropy at the beginning. But the entropy of what? The entropy of the best action in a set of cardinality size of A. So the entropy of that is at most log of the size of A, which is this thing. Okay, so what we're going to do this afternoon is I will give you algorithms which attain those bounds, and more importantly, I will tell you about the mirror descent framework and how it fits very well in this framework. Is there a question before we break for lunch? Yes?
If we look at the dot product you're using to factorize the
Yes?
stuff, can't one think about generalizing to nonlinear loss functions which have low complexity, in which case this would be analogous to doing some sort of nonlinear matrix factorization?
Okay, so I'm not sure exactly about what you're saying, but yes, you can use this for nonlinear losses, but yeah, it becomes more complicated. Maybe there is something easy to be done, but for instance, the first proof that Bandit convex optimization, you can do it, was an information theoretic proof, and doing some refinement of this, but it was not going through matrix factorization, because matrix factorization is a very linear thing to do. So in nonlinear settings, it seems hard, but yeah. Okay, let's go for lunch.